Hello, welcome to another online lecture for Philosophy 478. In this lecture, I'm going to introduce you to what's called correspondence theory. This is a general theory in the model theory of modal logic that studies what properties the basic modal language can express, what can be described with the basic modal language. Now, I'm going to assume that you've already seen the first video, or you've already been introduced to modal logic. But just as a reminder, recall that a model or a Kripke structure consists of three components, W, R, and V, where W is a non-empty set, R is a relation on W, so a set of ordered pairs. And as a reminder, if we have a state W and another state V, we draw an arrow from W to V just in case W is related to V, or a bit more formally, the pair WV is an element of the set R. So relations are understood as sets of ordered pairs, but I draw an arrow from W to V just in case W can see V. So the pair WV is an R. And finally, V is the valuation map that assigns the set of states where the atomic proposition is true. Now, given a formula of our modal language, we define truth as follows. First of all, if phi is an atomic proposition, so here P is an element of AT, the set of atomic propositions, so P is true at a state W just in case our valuation function says that it's true. Negation and conjunction are interpreted as you expect. And our modal formulas are interpreted as bounded quantifiers. So box phi is true at a state W if for all states that W can see, phi is true. So we're at a state W. We look at all of the states that W can see. There's a whole bunch of them. Box phi is going to be true at state W just in case phi is true at all of these accessible states. Diamond is an existential quantifier if there is a state such that W can see it and phi is true there. So consider the formula diamond psi. This will be true at state W if there is an accessible state in which psi is true. All right, so that's just a reminder of truth in a model. But what we're actually interested in is what's called a frame. And a frame is just simply a model without the valuation function. So it's just the skeleton of the model. So a frame is a tuple. It's a pair where W is a non-empty set and R is a relation on that set W. So it's simply just a model but without the valuation function. And we say that phi is valid on a Kripke model, or just a model, if phi is true at all states in that model. And we say that phi is valid, sorry, this is a mistake, ignore that. Phi is valid on a frame if phi is valid on all models based on that frame. So the idea is that you fix a frame F, so that's just a pair W and R, and I can look at all models based on that frame. So you might write it M sub F, which would consist of the same set of states, the same relation, but then some valuation function. So maybe V1, and then we look at another M prime F, so that'll be the same set of states, the same relation, but some new valuation function, V2, and so on. So saying that phi is valid on a frame means you quantify, essentially you're quantifying over all possible ways, all possible valuation functions, all possible ways of assigning atomic propositions to the different sets of states, or sets of states to the atomic propositions. And this will be denoted phi is valid on F. Now, just another bit of notation, we will say that a frame has a particular property, or is called a P-frame if the relation in that frame has that property. So for example, phi is a reflexive frame, provided that the relation R is reflexive. And as a reminder, what it means to be reflexive is for all states, so every state in the frame, W can see itself. So there's an arrow from W to itself. And that's true for all states in the frame. We say that a frame is called a transitive frame, provided that R is transitive. And again, as a reminder, what transitivity means is that for all W, X, and V, if W can see X, so you can make one step from W to X, and X can see the state V, so you can make another step from X to V, so every two steps can be replaced by a single step. There has to exist a single step that will take you directly from W to V. So if W is related to X and X is related to V, then W has to be related to V. Another property, so I'm assuming these first two properties you probably heard of. This property is a little bit less common, although modal logicians and epistemic logicians talk about it quite often. That's the property of Euclideanness. So we say a frame is a Euclidean frame, just in case the relation is Euclidean. And what Euclidean says is that if you're at a state W, and W can see some other state X, and W can see some other state V, so if W can see V and W can see X, then these two states have to be able to see each other. V can actually see X. And in fact, it's not hard to see just by the symmetry of this and right here that you get X and V have to be related to each other. So if W can see two states, then X and V have to be related. That's what Euclidean is. Another property, a bit more common, symmetric. So a frame is symmetric if for any state W, if W can see a state V, then V has to be able to see the state W. So if W is related to V, then V is related to W. And finally, a frame is serial if for any state in the frame W, there must exist a state V such that W can see V. So there are no dead-end states in a serial frame. So just to test your understanding, you should be able to prove that a frame is, well, let's say, actually, I think you just need reflexivity and Euclideanness, but certainly reflexive, transitive, and Euclidean implies that the frame is symmetric. So in fact, if the frame is reflexive, transitive, and Euclidean, then we know it's also going to be symmetric. That means the relation is an equivalence relation. And that's what you might call the typical class of models that epistemic logicians are interested in. Typical class of frames that epistemic logicians are interested in. All right, what we're interested in though, and I'll say more about these properties in class, but what we're interested in is the fact, and this is really an amazing fact, it's a beautiful fact about modal logic, that modal formulas actually can define classes of frames. So we say that a modal formula phi corresponds to a property P of a relation in a frame. So P might be something like reflexivity, or it might be transitivity, or seriality, what have you, provided for all frames, phi is valid on that frame if and only if that frame is a P frame. So you can think of this as if a property P has a a modal formula that corresponds to that property, then that modal formula defines a particular class of frames. So look in the entire class of frames. Some of those frames, so here we have, let's say this is the entire class of frames. Some of those frames are going to be reflexive. So this is the class of all reflexive frames. And it turns out that if we look at the class of frames that in which a particular formula is valid. In this case, box phi implies phi. We'll see that in a second. So if we look at the class of frames in which box phi implies phi is valid, that defines the exact same class. This is that's what it means to say box phi implies phi corresponds to the reflexivity property. So here are some basic results. First of all, like I just mentioned, box phi implies phi corresponds to the reflexivity property. Box phi implies box phi corresponds to transitivity. Not box phi implies box not box phi corresponds to Euclideanness. Phi implies box diamond phi is symmetric. And finally, not box falsum is seriality. So the easiest one to see right away is actually seriality. If you just sort of think about it, not box falsum says explicitly that it's not a dead-end state. So it's sort of obvious that corresponds to the property seriality. These other properties are a bit more surprising. So what I'm going to do in the remainder of this short video is just prove these first three properties. And I just want you to get a feel for correspondence theory, how this actually works. So let's go ahead and let's get started.